Alright, thanks for watching and welcome to one of my favorite proofs about limits, and it's something I call a duality theorem because it really illustrates the beautiful relationship between infinite limits and finite limits. And what I want to show is the following. So suppose, Sn is a positive sequence, so Sn is bigger than 0 for all n. Then Sn, so limit n goes to infinity of Sn is infinity if and only if the limit as n goes to infinity of 1 over Sn equals 0. So if s goes to infinity, then 1 over Sn goes to 0, which is not obvious because we have not shown any quotient laws for infinite limits. And that said, we can still prove very neat things. For instance, what we know, so in a previous video, I've shown that the limit as n goes to infinity of 1/2 to the n equals 0. So in particular, the limit as n goes to infinity of 1 over 2 to the n equals 0. But then, by this fact, this implies that the limit as n goes to infinity of 2 to the n is infinite, which is not an obvious result because remember, we don't know what logarithms are yet. So try proving it directly. It's a bit harder than you think. All right. And again, let's prove this, and it's beautiful because you need both definitions, infinite limits and finite limits. So, first do this. So suppose that Sn goes to infinity. In other words, we know that Sn gets arbitrarily large, and what we want to show is that 1 over Sn gets arbitrarily small. So let epsilon be 0 be given. And again, we know that Sn blows up, so in particular, we can say this is bigger than any m. In particular, we know that Sn is bigger than 1 over epsilon. And so let m be 1 over epsilon, which is positive. Then, since Sn goes to infinity, we know that there is some m, so some capital N, such that if n is bigger than capital N, then Sn is bigger than m. Okay. So that's what we know, but what we want to show is 1 over Sn is small, but then with that same n, with that same capital N, if n is bigger than capital N, then let's estimate the difference between 1 over Sn and 0. But that's just absolute value of 1 over Sn. And since Sn is positive, this is 1 over Sn. But look, Sn is bigger than m, so 1 over Sn is smaller than 1 over m. And remember, we had our choice. M was 1 over epsilon, so this is less than 1 over epsilon, which is epsilon. And therefore, it is true that 1 over Sn goes to 0. One over Sn goes to 0. And again, you can prove, you can guess the choice of epsilon simply by letting 1 over m is less than epsilon. So m is bigger than 1 over epsilon. All right, so that's on the one hand. On the other hand, suppose this thing is true. So 1 over Sn goes to 0. Okay? And what we want to show is that Sn is arbitrarily large. So suppose I give you a huge number. So let m be given. And in particular, if m is large, 1 over m is small. So let epsilon be 1 over m, okay, which is positive. Then, since 1 over Sn goes to 0, we know that there is capital N such that if n is bigger than capital N, then absolute value of 1 over Sn minus 0 is less than epsilon. So in particular, this becomes 1 over Sn is less than epsilon. And then for that same capital N, capital N, if n is bigger than capital N, we get that Sn becomes, you see, 1 over Sn is less than epsilon, so Sn is bigger than 1 over epsilon. But now we chose epsilon such that 1 over epsilon is m. So it's 1 over m, which is m. And therefore Sn is as big as we want, so Sn goes to infinity. How nice is this proof, really? Because it really uses both things, limits at the point, finite limits and infinite limits. All right, thank you very much.